Okay, I see that QCD people have showed up. I just want to give a disclaimer that this has nothing to do with QCD axion. Axion I am using very loosely. So by axion I mean any pseudoscalar particle. In particular, I will, especially now cosmologists are interested in very light pseudoscalar particles with mass much less than 10 to the minus 6 eV, which I think in QCD people are interested in. There's very light, so axion I mean any very light pseudoscalar particle which has a coupling to photons. Yeah. So axions I will mean just any pseudoscalar particle. And more actually need not be even a pseudoscalar. Most of the formalism or what I will talk about goes through even if it is a scalar particle. So this is just I will tell you maybe towards the end what this picture is, but this is one of the signatures of the axion that you can expect in the CMB sky. You make CMB map and you have seen CMB maps which has these all small fluctuations. But if there is a axion which couples to photons, then you will see one particular very characteristic pattern, an isotropic pattern on the sky. This is the picture of the sky. If there is an axion which has significant coupling to CMB, so by looking at CMB, so most of the talk will be about CMB. How looking at CMB we can constrain the pseudoscalar particles like axions. If you're going to axions, let me start with something a little bit more familiar, which is gravitational lensing. So we all know that light passes near a massive body, it bends. This is known as the classical picture is talk about geodesics, which are curved in the presence of a massive body. But we can also look at a quantum picture. In a quantum picture, we will say that it interacts by exchanging gravitons with the massive body, and it exchanges momentum with momentum of the photon changes. So what this means is this: in quantum picture, the graviton has a 2-photon coupling, and we exactly know what this coupling is from Einstein's equations. And in fact, so here we have some static gravitational field, and a free photon comes in and a free photon goes out. But we can change the picture, and we can say that there is an external electromagnetic field or magnetic field which is static, and a photon comes in and it can convert into a graviton. And again, this is again the same vertex which gives weak lensing, also gives us a conversion from a photon to a graviton. And it is also easy to see why we need external magnetic field, because we are converting a spin 1 particle to a spin 2, we have to conserve angular momentum, which means that this external magnetic field should be transverse to the propagation direction of the photon. So the longitudinal magnetic field has 0 angular momentum. So if there is a transverse magnetic field and you have a photon propagating, it can get converted into a graviton. But we don't really see this. There are limits on this because we know that the gravitation is a very weak force.
Why is the transversality argument any further?
This is to conserve angular momentum. We are converting a spin 1 particle to a spin 2 particle.
It's not possible to do it because if I just look at angular momentum component in the horizontal direction, then you don't need transversality.
No, the photon has no angular momentum in the no, photon has either angular momentum 1 or 0. Yeah, so in the direction in the propagation,
Yes.
photon has angular momentum of 1 or minus 1.
Yes. Oh,
And you are converting it to a particle which has the angular momentum plus minus. Yeah, these are massless. So everything is, yeah, this is a real photon. And in fact, you can actually get the same thing in classical also, classical general relativity also. And this is a very old paper by Gertzenstein. And you just write down the linearized Einstein's equations, and the stress energy tensor of the electromagnetism is a source term for the gravitational waves. So here it is this tau ik, which has this FLM. This is the Faraday tensor. And you get basically the same physics out. So conversion of photon. Okay. So conversion of gravitational waves into electromagnetic waves, it is again there in classical relativity. So now the question to ask is, so here we are converting a spin 1 photon particle to a spin 2 particle. Now suppose if there are other massless spin 1 particles or spin 0 particles, then can photon also get converted into those? And the answer is yes, if there is a coupling like this. Especially, so I will mostly talk about spin 0 particles, and spin 0 particles also you have the same problem that you have to conserve angular momentum. So you need it can only happen in the presence of a transverse magnetic field. So that is so spin 0 particle for me is I just take axion, which is a pseudoscalar particle, but most of the formalism goes through for scalar particle also, just so is a small change in Lagrangian. Okay, so we can, if there is a spin 0 particle that exists, then it could have a coupling like this, and so then this provides us a way to search for new spin 0 particles, and a lot of lab-based experiments and which rely on this, they are mostly looking at axions which are coming into your detector, and then they convert into a photon into a detector. But we will be looking at photons. So if you have a known source of photons which has for which you know the spectrum very well, the intensity very well, then you can look for disappearance of the photons. If you know what was created at the source and you look for disappearance, you can start constraining the existence of these massless or almost massless pseudoscalar particles. Okay, so why axions? Again, so I think there are lots of reasons, probably in string theory and also in supersymmetric theory, to talk about axions. There are experts on that, but in cosmology recently it has become quite fashionable, particularly because if the mass of the axions is very, very small, of order 10 to the minus 22 eV, or then if you calculate the de Broglie wavelength of such a particle going around in the galaxy, it is of order kiloparsec scales.
Why did it have to be pseudoscalar?
Need not be. I am just taking an example because mostly people talk about the pseudoscalars, but it could be a scalar also.
Yes. So, but the detector will.
So yes, I will talk about what will change if you replace pseudoscalar with a scalar. Something will change. I will briefly mention what will change.
And I mean, why are you focusing on pseudoscalar? Why is it important to look for pseudoscalar? And why is it more important to look for pseudoscalar? I mean,
Well, so okay. So one thing is that okay, in QCD, this axion was predicted to solve the strong CP problem. So from that point of view, from the standard model point of view, axions. It's more natural to talk about axions, but as I was talking with Tuhin, that in supersymmetric theories, so it's in a standard model, it is difficult to have a massless scalar particle. But if you go to in supersymmetric theories, you can have massless scalar particles also. But there is nothing sacred about pseudoscalar particles. You can talk about. I'm just talking about pseudoscalar because it is more fashionable and.
Well, the coupling with the electromagnetism also changes.
It will also change. Yeah. But as far as observations are concerned or the way the search goes, it does not change much.
Is it because FF dual is E dotted with B, right? The other is E square plus B square. That's not the same thing. One gives you conversion to electric to magnetic. The other.
Yeah, okay, I don't know how. So you're saying that if you have a scalar particle, you will not have this kind of 2-photon vertex?
No, you will have an E square plus B square piece. It's not E dotted with B.
Oh, that does not matter. That is fine. You can still have, from E square also you can have.
So free electromagnetic wave is not active wave. E dot E will be 0.
Right. No, but from E dot E also you can get one of the E comes from the electromagnetic wave, one comes from the external magnetic field, and you can still have conversion.
So I
Yeah, so the term in Lagrangian will change, but so you will have the, yes, I will talk about what will change as far as this two photon vortex is concerned. But otherwise, there is nothing. You can everything goes through for scalar particles also. So these low mass axions, they have been dubbed fuzzy dark matter because they have this long de Broglie wavelength, which means that you cannot really localize it to scales smaller than its de Broglie wavelength. And it turns out it could solve some of the problems in the cosmology in large scale structure. There are lots of reviews if you are interested. So again, I will. Okay, so for a pseudoscalar, you have a interaction Lagrangian which looks something like this, and the form of this comes from CP. From CP conservation, you want the interaction to conserve CP, and because A is a pseudoscalar, it is CP odd, and you can convince yourself that E dot B, if you apply CP to it, then this term is also a CP odd. So this full term conserves CP. And if you have a scalar particle, then this term should be the scalar particle will be CP even, and this particle. So here instead of E dot B, as Tubhin was saying, you will have E square plus B square. Otherwise, nothing much will change. Again, so you can, I think, do this exercise in private, that you reflect electric field and magnetic fields, and then apply charge conjugation, and the magnetic field remains same, electric field reverses, so the combination also reverses.
So the comparison with graviton is more appropriate for the scalar rather than pseudoscalar, because there, H mu would couple to T mu, where
so there also, yeah. So here, okay. So what this term tells you is that suppose you have a photon coming in. So suppose electric field is coming from the incoming free photon, is the polarization. B is the external magnetic field. Then only the polarization which is parallel to the magnetic field gets converted, couples. The other polarization does not. So only one polarization of the photon couples to the magnetic field. And for a scalar particle, it will be the opposite polarization which will couple to the scalar. For gravitons, you have two polarizations, and one polarization of graviton will couple to one polarization of photon, and the other polarization couples to the other polarization of photon. Okay, so you can write down, okay, this is just you can write down the wave equation.
What we're talking about is not really F mu, F2 mu, but F1 mu.
Yeah, F1 mu nu, F2 mu nu, right. So one F mu nu is coming from, let us say, your photon, and the other F mu nu is external. Yeah. Yeah, so it should be 1 or 2. Or I mean, you can say that, okay, each F mu nu has both components, and then you do a right. So this E and B, one E belongs to photon, the B is different. Okay, so solution to Maxwell's equations in vacuum is a free propagating waves. This is just some simple stuff. So you have energy which is equal to momentum. But what is important for us is, so we will be looking at electromagnetic waves, which is, so this is in vacuum, which are going through a medium. So in the medium, the electromagnetic waves acquire, there is a refractive index, which is just the momentum to the energy, ratio of momentum to energy. And if you have, this is not equal to 1, it means that there is a photon has effective mass, which is not 0. And you can relate the refractive index to the photon's effective mass, just using this relativistic relation. And for a medium which has some free electrons plus some neutral atoms, you can write down what is the refractive index. You can look in Born and Wolf, standard electromagnetic text, what it will be. It's basically you look at, you solve the classical electromagnetic equations in the presence of charged electrons. The free electrons are just free, and the bounded electrons are like oscillators, which are subjected to an external electromagnetic field. So these Wi's here are, so for hydrogen, Wi's will be the, if the atoms are in ground state, these frequencies will be the resonant frequency, the frequencies of transitions to higher excited states, and these are like many different oscillators, and you sum so you sum over all the oscillating frequencies. So the interesting thing here is that the refractive index is less than 1 if you have only free electrons, which means that the effective mass of the photon is positive. Whereas if you have neutral atoms, then above the resonance frequency, again the effective mass is positive, but below resonant frequency the effective mass becomes negative. So for a primordial plasma which has, let us say there is only hydrogen, if you ignore helium, you can put in the numerical values for hydrogen in the ground state and you get something like this. So if you have a mostly, you have ionized plasma which has ionization fraction which is, let us say, more than 1 in 1,000 electrons are more than 1 in 100 electrons are free, then actually the first term will be dominant. So you can ignore the neutral component. So we can plot this. This is the, so this is, so here I think these are the number density, this is the number density of electrons and number density of hydrogen.
So H means, is it hydrogen atom or ions or?
This is atom, it is the neutral atoms, only neutral atoms. NHE is only neutral helium. So these are free electrons, and so protons, because they are very massive, they don't really contribute much.
So after the ionization, because there are H plus ions and electrons, you will count the contribution in electrons,
But not to NH.
but not
Yeah.
F sub I is the ionized.
So these are free electrons and neutral. So NH over NE will be your, well, okay, if you add
F sub I, the ionized fraction.
Hmm?
In the second line.
Fi, no, this is not FI, this is oscillator strength. This is the strength of each transition.
So this is only
This is related to the
the polarizability of that.
Yeah, this is coming from polarizability of the atoms. So Fi is the strength of each resonance. Okay, so this is the, so I will ignore helium, and this is the good approximation for us. So if you start with very early universe, the universe is almost fully ionized, but at some point it recombines, which means that, and the ionization fraction actually drops below 10 to the minus 4, which means that the effective mass will start with some large positive value at high densities when everything is ionized, and then as when universe recombines, it may become effective mass will become imaginary, effective mass square will become negative. And then the universe will ionize again and again. So effective mass of the photons, so we can plot this. So this is the effective mass of photons as a function of redshift. So very high redshift, you start with some high mass, you start with 10 to the minus 6, 10 to the minus 7 eV. So again, so this term, if you see, this is frequency dependent. So high frequencies will become imaginary, but low frequency may still, this term may still remain same compared to, for frequencies much smaller than EV. The first term may still dominate. So this is what you see. I have plotted 3 frequencies. So for low frequencies, so this is the frequency today, but as you go higher redshift, this is basically nu times 1 plus z, for which I have calculated the effective mass.
So why is that called effective mass?
If you
because it's a
just
free formula with
so the effective index is defined as the ratio of this momentum of photon to the energy, and then you can apply your relativistic relation, and then so this is like effective mass. So it plays the same role as, but it can become negative. So it is not really, it can become imaginary, not negative, imaginary. So here, so for high frequencies, 500 gigahertz, it becomes imaginary around At recombination, this drop is recombination, but low frequencies remain real. At some point, universe ionizes again, and again all masses become real. So
that happens when that second term with omega square.
right. So if second term dominates, it will become imaginary. So at high frequencies, this term will dominate.
But I see. But aren't you doing some kind of perturbation theory here, or not? I mean, isn't this term something like a second order perturbation theory?
I don't think this is not really quantum mechanics. You are just doing solving classical Maxwell's equations.
There are no higher order terms here?
There will be, so there will be, I think, higher order terms. So at resonance frequencies, this goes to infinite. So then you have to look at, so that there's a correction which comes here. Then you put a imaginary part in the denominator.
What are omega
So-
i's,
so-
please? Omega i's are
Omega i's are the frequencies, basically transition frequencies of hydrogen atom, n equal to 1 to 2, 1 to 3, 1 to 4. So this is like oscillators that the incoming electromagnetic wave is seeing.
So this would be the same as the formula for electromagnetic waves, incident on oscillators of frequency.
Yeah. That's exactly what this is. For free electrons, there is no resonance frequency, so this does not appear. Okay, so in the presence of interaction with axions, we get a coupled system of equations for axions and electromagnetic waves. Again, so I have added the effective mass of the photon to the wave equation for electromagnetic waves, and then you have a similar equation for axions. Right. And then we want to look for solutions which are of again of plane waves, because we are a free photon is coming and then a free axion wave will go out.
Sorry, you probably said this before, but that mass term for the axion is like an expectation value of f wedge f in the background. Oh no, sorry. Yeah, why is that an effective mass term? I said that.
This is not effective mass. This is just the mass of the axion in the low.
The genuine mass of the axion.
In the low, yeah.
Okay, fine. And this n gamma squared is
the effective mass of the photon.
And where does that come from?
It's come just from, because photon is propagating in a medium, so it sees these oscillators and free electrons, so they respond to each other, and it requires a mass.
And sorry, the right hand side is where what
so this is the coupling. So this is coming from, okay. So we are looking at this kind of interaction between axions and photons. So this term gives you the source term in this Klein-Gordon equation for axion and for wave equation for photons. Okay, so
the one with H and He contribution, helium and hydrogen contributions.
sorry.
Okay, so I agree that there will not be a H plus contribution because there are no oscillators there. But there could be a He plus contribution.
Yes, I am just ignoring helium altogether. Yeah, in principle you can write here,
He should have two terms.
but when you are assuming that, so there will be a helium contribution, and if there is a helium plus, it will also contribute. But helium is a small fraction, so I am ignoring that altogether. Plus, we are looking at frequencies which are much smaller than the resonant frequencies. So then the resonance frequencies of helium are much higher than hydrogen, so this term is again suppressed by this omega i's. Okay, so we want to look for this kind of wave equation. So we can, if we can substitute this partial t delta by k square minus omega square, and we take the relativistic limit, so which means that the effective, both of these effective mass is much smaller than the energy of the particles. So we can replace k plus omega by 2 omega. Okay, so I think I did not mention earlier. So all of this is actually exactly what you get for neutrino oscillations. So the physics I will talk about from now on, it is exactly same as neutrino oscillations. All the effects that you get in neutrino oscillations, you will get here also. You will have resonances. So this formalism is exactly same. So yeah, so okay, so we get we take the relativistic approximation. So if we
Sorry, that BT is also a function of is BT.
BT is the external magnetic field.
Oh,
It is again a magnetic field in the medium through which the photon is propagating.
I see. So it's a linear set of equations.
It's a linear equations, yeah. So BT it does not belong to the photon.
Okay.
It is a external.
So it's oscillation in the sense that small a and a parallel are oscillating? Or
Yeah. So they will oscillate because it can convert into axion. Axion can convert back into photon as they propagate. Okay, so we can linearize this equation and we can again put one of the. So if you are looking at photons with definite energy propagating through a medium, so we can put a definite energy but keep the position dependence in this derivative. So we get a linear equation for. So linear coupled equations for axion and photon fields, and here I have defined these deltas, which are just effective mass squares divided by. So this is the mass matrix, and you get off diagonal terms in the mass matrix, which is coming from this coupling between axions and photons.
All those deltas are position independent.
No, so they will all depend on position because you are. So I will go through. First, I will go through the case where they are independent, and then you will what happens, and then I will see what happens when you are propagating. Because they depend on the medium, and medium is changing.
Okay.
As we saw, the cosmological medium, as you propagate, all this MA will remain constant because axion has a definite mass, but this term will change and this term will change. Okay, so you solve this equation by again same way you solve the neutrinos. So I will just use I will basically people here use the same terminology that neutrino that we use in neutrino physics. So I will talk about mixing angles and oscillations. So you diagonalize by rotation by angle theta, and this gives you a basically oscillating solution. So conversion probability for photon to axions turns out to be this. Then you have a mixing angle to theta, which gives you the amplitude of the mixing, and then you have a term which depends on. So here I am assuming that the medium is constant. So you have constant density and constant magnetic field.
Sorry, Rishi, you probably said this, but the background magnetic field is playing a crucial role here.
Yes.
Why is there a background magnetic field? Where are we looking at?
Yeah. So magnetic field you need because you are converting a spin 1 particle to a spin 0 particle. So to conserve angular momentum, you need something external.
We're talking about.
So it is in the galaxy or in the voids, or it could be primordial.
And there
So I will
is
talk
a
about.
significant background field, let's say between galaxies.
So we don't know. So
Oh, I see. So you're saying, yeah, were there to be a background? Okay.
so in our galaxy, we know there is magnetic field. So there we can talk about. So we can say what will be conversion probability given a value of coupling constant. But in the voids or in the cosmological, we don't know if there are magnetic fields. So what we will do is we will constrain a product of these two. So these two things.
What would cause them if they were there? Just some plasma or something?
There it could be caused by inflation, for example. It can create some seed magnetic fields, or even in the voids, you can have this outflows from the galaxies, which pump out gas into the voids, and this gas can carry magnetic fields with it.
Thank you.
Yeah, so I have actually converted. So photon has two polarizations. So here I forgot to mention. So I am looking at just constant magnetic field, which has a particular direction. Then only one of the polarization will couple, and the other polarization, the polarization which is parallel to the magnetic field will couple. The perpendicular polarization will not couple. So it reduces from a 3 flavor system to a 2 flavor system. Okay. Right. So these are just deltas. They are just mass terms, and then you have an off-diagonal term, which is the coupling. Yeah. So if you don't know what is the magnetic field, then you will basically look at the product of this. What if the product of these two vary? Because you can't talk about these two separately. But if you know there is a definite magnetic field, like in the galaxy, then you can just talk about G. Okay. So you solve this again. Coupled system of equations, and neutrino people have already solved this, so we can just take their solution. So this is so you have a mixing angle which depends on this magnetic field and the coupling strength, divided by what is I call this oscillating frequency, delta square oscillator, which is difference between electron and photon terms plus this mixing term. So this delta oscillation will determine the oscillation length. So this comes in this second term. So you see that there is a dependence on z here. Z is the direction is the along which you are propagating. So as you propagate, you will oscillate between photons and axions. So this is I have shown here. So the solution is basically that you have a amplitude which is given by this mixing angle, but as you propagate, you oscillate between axions and photons. This is exactly what happens in exactly same as the neutrino flavor oscillations.
So this mixing angle depends on the product of the.
So this mixing angle depends on this delta gamma A, which is magnetic field multiplied by this coupling constant and divided by this delta oscillation, which is this factor. So if you look at, you can look at different limits. Suppose axion mass is very, very small, so you ignore this. And suppose the coupling strength is also very, very small, then you see that it is suppressed by electron density. So delta E is proportional to the electron density. It is the effective mass of the photon, which is proportional to the. So in the high density regions, this will be very, very suppressed, which means if you want to look at this effect, the best places to look will be very, very low density regions. So you want regions, so it is proportional to magnetic fields. So you want to look at regions which have very high magnetic fields and very low electron density.
This axion mass is important for your, I mean, can you put that equal to 0? Or
No, it will be important. So you can, if delta E equals delta A, you have resonance and you have the maximum for. So I will talk about resonance a little bit later. If you have resonance, then you have got something same as MSW effect. So you can have a complete flavor conversion. So the mass is important. Okay. So this actually, so this system actually you can map it to a problem where you have a spin system with some magnetic moment, which is precessing in external magnetic field. Which initially this magnetic field is in a slightly different direction than the magnetic moment, and it will apply torque on the magnetic moment. So this polarization vector, the magnetic moment will basically precess around the magnetic field. And that is what is happening here. So in you can map it to this, where you identify this projection of the polarization vector on the z-axis as being a photon if it is completely along the positive z-axis, or a axion if it is in the negative z-axis, and the x, y directions have the phase information. So the projection of, so this will precess, and the projection of this on the z-axis will change, and basically you have the you have oscillations. And this B, this is not the same B, so this is a different B than this. This is just some hypothetical B where you have mapped our problem or two flavor problem into precession around a magnetic field. And the magnetic field is offset from the z-axis by an angle, mixing angle, which is 2 theta. Okay. So now we can actually write down the dispersion relations for these equations. So we put in, we substitute this k square minus omega square and look for solutions. So it will have solutions if determinant is 0, you will have non-trivial solutions, and that gives you the dispersion relations, the relation between omega and k. So these are the two eigenmodes of the Hamiltonian. So what I have plotted here is this two eigenmodes, M effective, which is 2 omega, omega minus k. So let us see. So if you go to very, very high electron densities, so I have taken axion mass here, which is, I think, of order some 10 to the minus 12 eV or something, which corresponds to photon mass around 10 to the minus 7 centimeter cube, this particular photon density. So if you go to very, very high densities, then one of the eigenstate converges, becomes almost completely a photon, the other eigenstate becomes almost completely a axion. But as you change your density, go to zero density, then you have one of the first eigenstate, it actually it goes towards an axion, and the second, the state which was axion, it in the vacuum, it okay. So let us say, what is the right way to put it? So these are the two eigenstates of our Hamiltonian. At high densities, very, very high densities, you will recognize the very high effective mass eigenstate as a photon, because that is what photon is, whereas axion has some one particular mass. In the vacuum, the photon mass will go to 0. So we will recognize this lower eigenstate as a photon, whereas the upper eigenstate we will recognize as axion. So now, and there is a resonance at a particular value when photon mass equals axion mass, and here there is a small gap between these two eigenstate. So now, so the previous solution that I showed you was in a constant. You have oscillations when you have everything is constant, the background is constant. But in reality, that is not the case. Actually, photons propagate in a changing medium. Then you have to ask whether it encounters any resonances along the way. And if there are resonances, then whether it will keep following the same eigenstate or whether it can jump to the lower eigenstate. And that will determine whether, in the end, whether we will detect a photon or an axion, or what is the probability of detecting a photon or an axion.
It's like in Kibbles array. It's like in Kibbles array. Landau-Zener.
Yeah, so these are Landau-Zener.
So which is a simple model of Kibbles array. Okay.
Yeah, so I will use the Landau-Zener transition probability to calculate what is the probability of going. So again, so we can define, so what will determine whether, so adiabatic, whether you remain on one level or you jump is whether the evolution is adiabatic or not, which means whether the Hamiltonian changes much slowly compared to the oscillation length. So we want to say whether this mixing angle is changing slowly or faster compared to the oscillation length. If it is changing much, much slowly, so we can define an adiabaticity parameter gamma. If it is much, much bigger than 1, then you are changing very slowly. And then the adiabatic theorem in quantum mechanics tells us that you will remain in this upper eigenstate. Whereas if you change if you change the change in the Hamiltonian is faster, then there will be some finite probability of you are transitioning to the lower level. So again, see all the discussion, I will assume that we produce photon at very early universe in very high densities, and then we are coming down to low densities. Okay, so we can write down this adiabaticity parameter. We have this formula for oscillation length as well as the oscillation frequency and also the mixing angle. So if you are adiabatic, which means you will always remain in this eigenstate. So it does not matter what you do as long as the evolution is adiabatic. Actually, what matters finally is the initial mixing angle and the final mixing angle. What happens in between is irrelevant, because you always remain in the eigenstate. So in that case, there is an analytic solution which just depends on the initial mixing angle when you produce the photon and the final mixing angle when you are trying to detect the photon. And you can see that if, let us say, we did, let us say initially we produce photon at very, very high densities, so 2 theta 0 is 0, but then you detect in vacuum, so 2 theta is pi, and the propagation was adiabatic, so we can use this formula, and this gives you 1. So if you adiabatically evolve from high densities to vacuum, the photon almost completely converts into axion. This is very, this turns out it is very powerful. It is actually, because you are only concerned about what is happening at the resonance point. It turns out it gives the strongest constraints on the axions. Okay, this I will skip over. This is just to show you that there are many others. So this is a very general system that we are solving. We are solving a 2-level quantum system in which there is a mixing between the flavors. And there are many different scenarios. The neutrinos I mentioned. There also, you can look at photons with 2 helicities which are propagating in a medium with a magnetic field along propagation direction. Then these 2 helicities have different masses. And again, if the magnetic field reverses sign, then when the magnetic field is 0, you will have degeneracy. So you can flip the helicity of photons. And this has some implications for Faraday rotations that astrophysicists use to learn about magnetic fields in the galaxy. And you can talk to Basu if you want to know more about this. So what happens?
So between the slow and the fast variations, there is a whole range of possible rate of variation of this parameter over this region. So
what do you mean?
Between slow and fast, you need not be just very, very slow and very, very fast.
Yeah. So then you have to talk about Landau-Zinner probability.
So
no.
There's a whole range of final
Yeah.
products.
No, I think what
No.
slow and fast mean are the higher energy state and the lower energy state of the quantum system. That's all.
This okay. This
Say that it has to be very fast or very slow.
this slow fast is not the change of Hamiltonian. This is just they call one mode fast slow mode and one mode fast mode. Why is this?
Just
I don't know.
frequencies are different. So one has a
But this is
frequency,
exactly the same as our this plot. So one eigenstate is going like this, other eigenstate is going like this. So if you go adiabatic,
Fractional conversion, that fraction.
yeah, that will depend on how fast the Hamiltonian is changing. Yeah.
Yeah, that will depend on the speed.
Yeah. Okay, so we can talk about what is the adiabaticity parameter. So here what I have plotted, again it will depend on the frequency because our this delta E depends on frequency, the photon delta E parameter that we have defined. So I have plotted here gamma A equal to 1. So I put 1 here and I put the value of B times G for which this thing will be 1 because we know what is how the electron density is varying in cosmology, at least on average. So we know this denominator. I set this equal to 1 and I plot this G times B combination which is in this. And it tells you that if your magnetic field or your coupling is greater than some threshold, then you will have a adiabatic evolution, otherwise you will have a non-adiabatic evolution.
And all that matters is how much that was when the 2 masses became almost equal.
Yes.
So it,
Rishi, is there a length scale also in the problem? Now you're talking about.
So length scale is the oscillation length.
But the length scale associated with the variation of the electric of the number.
Yeah. So that is coming here. So in this adiabaticity parameter, I have defined a gradient of this. So the delta is gradient of delta E. Delta E is the
So
electron
this will
density.
be like the peak of the power spectrum or something. This term will be evaluated in some average sense, RMS sense. How do you
why do-
evaluate this? The gradient of that.
So I am evaluating it for the average electron density.
So some RMS gradient will calculate over the path length.
No, so here I am just using average cosmological density because fluctuations are small for most of the evolution. It is 1 part in 10 to the minus 5. like universe is almost homogeneous. So then the gradient is coming just from expansion of the universe or the because the plasma is recombining. So I am not talking about what is happening with fluctuations. Yeah, so in principle you should, I have not, one should check whether they make any difference or not. I have not done that.
So normally also that's a function of distance as you pointed out. It turns out that the places where gamma 8 will actually affect your conversion will be in the region near the resonance. So what is the value of gamma AD away from the resonance is normally redundant. When you take only some reasonable area near the resonances.
Think of this problem in the sense of doing an integral, and only the saddle point contributes. The saddle point is where they are closest.
Okay, so this means this again provides us a way because we see CMB photons, we don't see that all of them have disappeared, which puts the upper limit on what this G times B can be. So this is one way of constraining this coupling and also the primordial magnetic fields.
Suppose half of them were converted to axions, would we have known?
Yes. We know that less than 1 in 10 to the 4 photons have converted because we see the spectrum. They will change the spectrum of CMB, and we see the spectrum of CMB, which is black body, which is what it was initially. So I will show the spectrum, what will happen to the spectrum when you start converting photons.
So just to understand that clearly, so you know what the spectrum was early on. You have to be able to see that there was a change in the density.
Yeah, so for early on you know from theory that early universe everything was in equilibrium. So CMB photon was a Planck spectrum, CMB spectrum was a Planck spectrum.
I see. And you're saying that, that had this been, had some of this attenuation happened, it would have happened in a frequency dependent way?
It will happen in a frequency dependent way.
Take this out of Planck.
Yes.
I see. So that you can clearly.
That is why CMB is so powerful, because other sources we don't know what is the initial spectrum, but CMB we know exactly what the initial spectrum should be. Okay, yeah, so we are talking about level crossing probability, and it is actually given by this, again, adiabaticity parameter at the resonance. So if it is much, much bigger than 1, then the level crossing probability is 0, and you remain in the same level. So this is again, this is the solution for the crossing probability in the limit when you assume that you can approximate the change in the electron density as a linear function of time or distance. And if gamma is close to 0, then this probability becomes 1, and you transition to the lower level with probability 1. Okay. So I showed you this effective evaluation of effective photon mass. So if you look at one particular axion mass, let us say 10 to the minus 11, and you see that as the CMB propagates through the universe, expanding universe, it will become equal to this axion mass at one point in time around redshift, around recombination. So you will encounter one resonance. But if you are, let us say, if you look at axion mass 10 to the minus 13, then actually you will encounter multiple resonances, 1, 2, 3. And if you look at higher frequencies, then even for arbitrary small mass, because this mass is becoming imaginary, so for arbitrary small mass, you will have a resonance at very high frequencies. But low frequencies, usually you either acquire one resonance or you acquire 3 resonances, assuming you detect in vacuum. So but actually we are not in vacuum, we are in the galaxy. So you should take into account that from this, this is basically the average density at redshift today. And then from this average intergalactic space, the photons should travel to us. And we are situated in a galaxy, which is again a high density region. So again, photon will, so we are basically at a density of around 10 to the minus 3 particles per electrons per centimeter cube. So we are in a hot, solar system is situated in a hot electron bubble. I have plotted this effective mass of local bubble here. So as the photons propagate from the intergalactic space to us, it will encounter additional resonances. So now we have to keep track of all resonances and whether you had the transition probability, whether you stayed in the same level or whether you transition to the other level. And if you are careful in your accounting, then in the end you can have a net probability of whether you see a photon or a axion. So level crossing probability. So again, so I will assume ignore interference terms between resonances. So I will treat these level crossing probabilities as classical probabilities, and this is justified if, for example, we are looking at primordial magnetic fields which are stochastic. So we are propagating through a stochastic magnetic field, and that will destroy any coherence that is there. So for a single resonance, we can say that if you start at, so ij are the probabilities that you are in the upper eigenstate or the lower eigenstate, the two eigenstates, and n index is the number of resonances. So if you have only one resonance, you start at initial 0, and after crossing one resonance, this matrix gives you the probability that, so p is the probability that you, off diagonal terms give you the probability that you cross the level, and then 1 minus p is the probability that you remain in the same level. And you have many resonances, you just multiply these probabilities, and you can again write down as in terms of a net probability which has the same form, and the you can solve for p here. So now we have to be careful, because suppose, so p is the net level crossing probability that you started with a, let us see, I have it here. So let us go back to this. So you encounter, so you are going back and forth, density is sometimes increasing, then it decreases, effective mass is changing. So you are going back and forth, and you are encountering resonances. So in the end, if you encounter, so you started here in the high density region, if you encounter an even number of resonances, then you are back on the same side of the resonance, which means that you will make a axion if you crossed a level. So the conversion probability is proportional to p. Well, in the odd case, you will end up on the other side of the resonance, and then you will have axion if you did not change level. So the conversion probability will be depend on 1 minus p. Okay, so this, okay, all of this was mostly review. Sorry? No, these are now relativistic particles. These are not dark matter axions. So I am converting CMB photons to axions, and CMB photons have energy which is much, much bigger than axion mass. So I am looking at the relativistic particles.
But is there any chance that there will be interference terms between?
So interference terms will not, so as long as the resonances are far away compared to the oscillation length, and you are propagating in some stochastic medium, then the interference should wash out. I have not checked it. I am just assuming here for now. But yeah, this is something we should check in future. But here I am, yeah, so this I think you should solve numerically and then see. So I looked at many, so people look at a lot of quantum systems. This is a very general problem. In atomic physics also people look at these quantums where you have periodic resonances. So you go back and forth. And there, if you look at older papers, people were assuming that there is no interference, but then people started looking more and more carefully, and they found that even when you are, the resonances happen many oscillations lengths apart, even then there is interference. But it goes away if you have some stochasticity. So here, yeah, so here because you have primordial magnetic field which is stochastic, and it will basically, it will change also direction. So you will interfere, the axion will mix with different photon polarizations as it propagates, so the coherence will be destroyed. So that is the argument. So these guys in 2009 applied this to, basically applied this theory to CMB, and they put limit on, so as a function of the mass of axion, you put a limit on g times b. B is in units of nanogauss, and this coupling is of order 10 to the 10 GeV. It should be GeV inverse, I think. Wait, oh, this is times 10 to the 10. Okay. So yeah, so you see that, okay, you put limits on these, which are, I will show later the limits on these couplings from ground-based experiments, which look at solar axions, and these limits are comparable.
Is it what upper bound?
This is the upper bound. This is the upper bound from coming from CMB.
This sort of bound should depend on not only the photon axion coupling and the magnetic field, but also on the set of non-adiabaticity parameters.
Yeah. So that is where it is coming from. So you calculate what is the level crossing probability for each resonance, which depends on the adiabaticity parameter, and that gives you the limit on the adiabaticity. So this limit is coming from adiabaticity parameter. Adiabaticity parameter proportional to g times b. So you are saying that it should be smaller than some value if you are not to convert all CMB photons into axions, and that gives you the upper limit. I don't know what this is. I think this is just some.
Two different places and they've tried to stitch them.
I don't know. Still, this should not go there.
Like these are two bounds coming from two different places and they're just trying to superimpose them and get.
I think this is just bad plotting. I don't know what is this.
And
I don't know.
this is a limit of g times b square, where b square is the local value of the magnetic field where
Yeah.
the resonance takes place.
Yeah. So it is actually it is redshifted to today. So all limits are in terms of today. So you redshift it by multiplying by 1 plus z square. So
But it's conceivable that b is very widely varying in the universe, right? So you just happen to.
yeah. So this is what they are doing is RMS value.
Yeah,
So-
average.
So this is stochastic
At a particular z,
at particular z. Yes.
the z at which the two masses
Yes.
cross
Yes.
each other.
Yes.
So it could be.
So what is the RMS value of magnetic field at that
at that
redshift?
z?
That's right.
It could be that b was very different before that, after that. It's only this one that matters.
Yeah. It depends on where B is coming from. If it was primordial, then it should just redshift as radiation.
But for multiple,
If it is some local,
there are many places where this is happening.
yeah. So then you should add up all these star level crossing probabilities.
So that plot is for the single resonance.
This, I think, in this plot, they just took the most adiabatic resonance. So it turns out that if there are many resonances and some are more adiabatic than less, then the most adiabatic resonance will give you the strongest bound. The net bound is almost same as what you get from the most adiabatic resonance. I think that is what they have used here. But you can take into account all resonances. So you can get the net level crossing probability from all resonances and use that. But then this B will be something which is some average. It is
In some sense, that P should be able to write it down in terms of mass of axion and effective mass of
which B?
that P, external magnetic field. Since that is going to be the external magnetic field at the resonance, we may be able to write it down in terms of axion mass itself.
No, axion mass drops out. It depends on this electron effective mass. This adiabaticity parameter.
I thought the actual
So everything-
is independent.
Uh,
It's fundamental constant. So you can vary them separately.
Yeah, you can, but now that B is plotted
Yeah. So that is why.
Be in terms of the remaining parameters, right? When
Yes,
you
yes.
satisfy certain
So that is why you have plotted it in terms as a function of this axion mass.
I'm
So at different redshifts, different mass will be in resonance.
I think you mean electron density and its derivative, not the maximum.
inner density and yes, sir.
So instead of the average RMSB, you can put some function of electron density.
Right, 3 times.
Why you're assuming the B is caused by an electron
No,
density?
because there is some relationship that relates electron density, magnetic field, and the axion mass. And
This
that's
is
the
what-
resonance condition.
No, but electron density we know
At the resonance?
at the resonance. Because here this is just the cosmological.
Assuming that you know B at resonance in electron density. Is that-
No, you know.
Either of these two you should.
No. Yeah, so you know electron density at the resonance, then you constrain what B can be.
I thought the resonance was essentially the two masses crossing each other.
Yes.
So that's essentially independent of B.
No, but
Yeah.
the mass of the photon is dependent on electron density and other things.
Just electron density, I thought.
Yeah,
not B.
just electron density.
So I thought that the electron density sets the mass of the electron.
Okay. Of that
Of the
electron,
photon.
of that electron depend on B, not the diagonal.
Right.
Not the diagonal. Yeah,
Right.
yeah, B is only in the mixing
Only the
out diagonal
Yeah.
terms. Okay, so these guys only used one resonance. These guys tried to use multiple resonances, and they claim that this range of mass is completely ruled out, but they actually messed up in their bookkeeping. So they used 2 resonances, but then they used cases where you have 2 resonances, but then they assume that you detect in the vacuum, which is not the case. You have 2 resonances, you are detecting it in the high density region. To detect in vacuum, you should pass through an additional. So they used the wrong formula, and instead of getting 0, they got 1, and they ruled this out.
So the result is
Hmm?
result is ruling it out or no?
Yeah, so we looked at it, and so this bound is wrong.
In this region.
In this region, this is wrong. So here they did not use, they used the correct formulas here and here,
So here.
but in this region they messed up, and instead of getting 0, they got 1 in for
Any
conversion.
discontinuities because of that in the bound? There curves.
Yeah, so in curves, so they are using slightly different different formalism here than here. So here, yes, there will be discontinuity because here you have no resonance. So here actually it will be below 10 to the minus 14. So here there is no resonance. The only resonances are coming from this high frequency thing. So you are using slightly different data here and here. So there will be some discontinuity. But here where you have resonances, I think these curves should, you should just extrapolate these curves. This limit should be something like this, instead of completely ruling out this region.
No, but it's always odd number of resonances, no? The resonances are always odd.
It depends whether you detect in high density region or, because we are living in actually a high density region. We are compared to this axion massive, so net resonances that you will have will be even when we are detecting something in the solar system. Right, so basically, yeah, so they made very strange statements that you have very strongly non-adiabatic resonances, and then they even number of resonances, and they close this window, but that is not true. But anyway, so this is okay, just saying that again. So initially people were also interested about using this photon to axion conversion as a explanation for dimming of supernova. That is, some of the photons that can get converted to into axions while coming from supernova to you, they will look further away, and you will infer that there is dark energy. So these guys again looked at CMB. So they looked at what kind of magnetic fields and electron densities you need in order to explain dark energy by this conversion of supernova light into axions. And these are these lines, horizontal lines. So I think this horizontal red line is what you need to explain dark energy, and this is ruled out by CMB. in this region below 10 to the minus 9. So, this is the CMB upper bound is this curve.
And the nature of the explanation is that there's some dimming in intensity,
Yeah.
which you might
You lose.
misinterpret as things going very far away.
Yeah.
But actually is because of this. That's
Yeah.
That's the section.
So you interpret
the
it as dark
acceleration
energy.
is not really there.
Yeah.
Things are nearer than
Yeah, because
I see.
yeah, at that time the
That's only one of the.
yeah, that is only one of them. But this was 2002, where people were thinking this was still the strongest strongest evidence for dark energy. But again, this is ruled out by CMB, at least for the low electron densities, and here it is ruled out by other things. Anyway, okay, but okay, this was just the background and a few things about old papers. So the main focus of this new paper that we have written is what happens in the galactic field of the Milky Way. Because people were earlier only talking about extragalactic magnetic fields, which we don't know if they exist or not. So you can only constrain a combination of magnetic field and coupling. In the Milky Way, we know magnetic field exists, and we also have idea of what is its magnitude. We can actually, so one unknown goes away, at least at some level. There is still a lot of uncertainty in this.
And how do we know what these magnetic fields are? Just roughly.
So this you look at synchrotron radiation, which is energetic electrons going around magnetic fields, and you look at polarized. It is synchrotron is polarized, so it tells you direction of magnetic fields. You also look at Faraday rotation, so you look at extragalactic radio waves and how their propagation through the galaxy affects them, affects the different frequencies, and that gives you idea of what is the line of sight component of magnetic field and also what is the electron density in the galaxy. So this is just a cartoon model of galaxy. So this inner circle is our galaxy or our galactic halo. Well, inner circle is our solar system. So solar system we think is in a hot bubble. The electron density of this 10 to the minus 3 per centimeter cube is for a micro Gauss magnetic field, is fully ionized bubble. And then you have, our solar system sits in a galaxy, which galactic halo has a size of order 100 kiloparsec. And again, the density in the center of the galaxy is very high. It goes to about 10 to the minus 1 per centimeter cube, and it goes to 10 to the minus 5 as you go to the edge of the galaxy, galactic halo. And then if you go to the extragalactic medium, it will reduce even further, and at some point it will become equal to the cosmic average. It's 2 times 10 to the minus 7, and then if you enter a void, then it will reduce even further below this. But this part is very, very uncertain. This blue part and pink part we know a little bit by looking at different astrophysical observations. We know about both the electron density and the magnetic field. So we want to see what we can learn about axions by looking at conversion of CMB into axions in the galaxy.
I mean, the blue circle seems to say that if we go out of a solar system, then the electron density
increases
by
yes.
a factor of 100.
So we are sitting in a special low density region, which is surrounded by some high density interstellar medium.
What is NG?
Nanogauss.
Wait,
This is the magnetic field. So magnetic field outside the galaxy, we expect.
Estimates.
Yeah, these are estimates. So this we know more or less confident that inside galaxy it is micro Gauss, but outside galaxy we only have upper limits, which are of order nano Gauss.
Okay.
So this is what galactic magnetic field looks like. So again, so what I will be using is very simple models of galactic magnetic field, just to see what kind of signatures we can see in the CMB. In the future, our knowledge, so this is, these models are calculated using very sparse data on the sky. So we don't have data, we don't have a continuous coverage of the sky for all observables. For synchrotron, we have continuous, but like Faraday rotation, we only look at point sources. But still, people have come up with simple models which fits all current data. But in future, we will have more and more observations, especially with the square kilometer array, and we will have a better model of the galaxy, and then we will be, so we could do a little better. But for now, this is just I am using the current best model that we have, just to see what kind of whether it is interesting or not to go to higher model or not. Or
What is the dot?
dot is I think our solar sun. So this is 5. So this is the x direction in the galactic plane, and this is the out of the galactic plane, and this is the poloidal magnetic field. So it goes like, so our galaxy is here, and this is the magnetic field like this. Again, so this is I think a dipolar magnetic field, but now people think it should be something like a quadrupolar pattern. But I will be using this. So this is just showing a section through the center.
And roughly speaking, this is caused because things are ionized and going around. There's a current.
Yeah, so that is the dynamo mechanism, that you have gas which is going around, which is ionized. So it converts, if there is a small seed magnetic field present, then it can convert kinetic energy into magnetic energy.
And
there's
you break the plus minus symmetry because electrons move faster than protons.
Yeah. Okay. So this is one component of the magnetic field, and then we also think that there is in the plane of the galaxy also there is a magnetic field which is going around like a torus. So these are the two components that we will take, and the strength is of order microgauss. And then for the electron density also, we know, again, there are model with many components. Most of the components are important only close to the disk of the galaxy, where electron density is very high, so our conversion rate is suppressed. So we are not interested in that region. We are interested in regions which far in the galactic halo, where electron density is very, very low. So there, for that we need only this thick disk component. So this is as a function of radius, and this is as a function of as you go above the galactic plane. So only the one component which is important as you go few kiloparsec. So this is like an exponential profile of the electrons as well as the magnetic field as you go further and further out. So now if you look at this cartoon, so between 10 to the minus 5 and let us say 10 to the minus 1, the photon mass is between 10 to the minus 11 and 10 to the minus 14 eV. So for axion mass between this range, you will have resonances. So we can look at resonant conversion of CMB to axions. Again, so I told you that the spectrum is different. So the change in the CMB intensity is just the probability that CMB photons converted into axions multiplied by the original CMB intensity. And this probability for the resonant conversion is proportional to frequency. So we can plot this. So this polarized axion signal looks sometimes this like this red line. There is the Soniev-Zeldovich effect, which is this violet line. Then we have some dust in the galaxy. And this black solid line is the CMB anisotropies. This is the black body part of the CMB. So see, so here we have actually a little bit of problem because this polarized axion, which proportional to omega, it is actually very close to the CMB anisotropies that we see. But if you calculate where, so when we are looking at our galaxy, then because there is a some profile of the electrons and as well as magnetic fields, and when you look in any direction, then only the transverse component of the magnetic field matters, and it is also will change when you look at different directions. So both the electron density and magnetic field pattern combine to give you a pattern in this CMB distortion that you will see. So you can basically make a contour of, let us see with orange, a constant electron density around the galaxy or constant photon mass. And then at different resonance, we only need to know about magnetic field at these points on this circle, and that will give you a pattern on the CMB sky. So this is what we have calculated for this mass of 5 times 10 to the minus 13 eV. And it's very interesting pattern. There is no foreground or no other cosmological signal which looks like this. So actually, if you see something like this in CMB sky, it is a definite signature of axions. And yeah, so galaxy is, this is the galactic plane. So there is a asymmetry, and that is probably because the model, I think, in the southern hemisphere is not very accurate of the galactic magnetic field. So again, but this is the model that we have. So there is some asymmetry in the magnetic field, which shows up in the asymmetry in the this axion pattern also. And again, for a different axion mass, we will get a different. So this is the fractional change in the CMB intensity that I have plotted on log scale. So the signal will change, but also the pattern changes a little bit. So by looking at the pattern, we can even tell what is the axion mass if we see something.
In your spherical shell kind of rough model of galactic magnetic field and electric density, there is the central shell, the solar system is slightly offset, right?
Yes, our solar system is here. It is 8 kiloparsec away.
Yeah. So does that offset? How does that reflect into this pattern?
Yeah, so
If it was not offset, what would have got something?
If we were closer, I suppose these would go closer to the poles, the two blobs.
Just to get an idea of.
right. So here still this is the galactic center. So this symmetry is just that symmetry when we see the galaxy, whether it is symmetric or not. Because we are at the center, when we look at the center, we see this strong magnetic fields. But when we look at the anti-center, then there are not much magnetic field. So the signal here is weaker compared to here. If we were at the center, then I think this will become independent. So this is the longitude. So longitude. So this direction is when you looking like this. So this asymmetry will go away. You will have just a planar pattern if you are at the center of the galaxy and you have axial symmetry.
Are we exactly on the galactic disk or slightly above or below?
But that does not matter. We are 50 parsecs above. But at the level of accuracy we are working here. So again, so we can do some forecasts for the future experiments. What is the chances of seeing such patterns in the sky? So these are all CMB experiments: Pixie, Lightbird, Core. So Pixie was a American experiment. Lightbird is Japanese. This is European mission, and they can do quite well compared to current ground-based experiments. But of course, ground-based experiments will also improve next 5-10 years. So we.
Why did you choose roughly this mass of the axion?
This is in the center of the range where we have resonance. So slightly, yeah. So we did not do the for whole range of masses. We just did for few axion masses. So for smaller axion masses, we have a slightly stronger signal because the electron density, the resonance happens a little bit further away when the electron density is smaller. That is very, very weak. So you can try to
associate with that also there would be some characteristic pattern.
Yes, but that will be much, much weaker than this because you know what is the gravitational coupling. We can, that is actually many, many orders of magnitude smaller.
So this already factors in improvements coming from SK for our local magnetic.
No.
So
But so this assumes we know, well, this is actually a very crude estimate. So it does not use all the information that we have. It is just some Fisher matrix analysis using the spectral information. So in principle, if we know our magnetic field much better and we take into account all the information there should be possible to do. So this is slightly conservative estimates. It should be possible to do slightly.
This pattern has not gone into this calculation?
The pattern has gone approximately in the sense that we assume that because of this pattern, we can distinguish between So because it is polarized and it has a pattern, we can distinguish between CMB and axion. So we don't marginalize over CMB. We just assume that CMB can be removed because of this. So we take out some of the components. We don't marginalize over thermal SZ because we also say that we can, because of this pattern, we can just distinguish it completely from that. The only thing that matters is dust, because dust is still, because this signal is near the galactic center and dust is also near the galactic center. So we marginalize over dust. So that way, in some approximate way, it has gone in. But we have just used some average signal. So for these constraints, so see the signal varies a lot. It goes from 10 to the minus 7 to 10 to the minus 10. We just made some average signal, took the average amplitude over cleanest part of the sky, and just use that for the Fisher-Cap matrix. So it is a little bit conservative. It could you could do a more careful calculation. So we just wanted to see if it is interesting or not.
So I wanted to get a sense of how this accuracy compares with the previous things you told us. So suppose B in that, which was unknown, is taken to be the same order of magnitude as what it was here. Then are your sensitivities basically comparable?
Yeah, so B there they are assuming nanogauss. So if you say that B, we know B outside is nanogauss, then they were talking about this 10 to the minus 1 or so, whereas we are looking at 10 to the minus 3, 10 to the minus 4. But
that was G, this is G squared?
This is G square, that was, let me see. This is G, but at around 10 to the minus 1 it is same. So G square will be 10 to the minus 2. But again, so this line, okay, maybe, I think we are already out of time. So this is actually very, very crude. So we also think that this estimate from CMB is not correct, because they assumed very simple model of voids. They assume that you have regions of megaparsec scale. You have magnetic field first in one direction, then it abruptly changes in a random direction, then it again abruptly changes in random direction. And then you have decoherence between the domains, and you add up the probabilities, and that gives you these kind of strong constraints. But this is not a very good magnetic fields. We expect to be some power spectrum with some stochasticity. So you should really calculate the adiabaticity parameter for the also for the non-resonant case. So if you are if magnetic field is changing over megaparsec scale, it is much, much bigger than oscillation length, which means that you will have adiabatic evolution, and what will matter is only the initial point and the final point. What matters in between will not matter.
And here, what the axion mass was approximately?
I think they took around 10 to the minus 11 or 12. So this is not a resonant convergence. So axion, this is not sensitive to axion mass that much. They are just looking at non-resonant conversion. So you have a little bit of oscillation, and then abruptly magnetic field changes, and again you have little bit of oscillation, and again it changes, and then you have decoherence. So you add up the contributions.
So you're getting at least comparable accuracy.
Yeah.
Probably.
So we did a slightly better estimate. So this is for the voids. So we assume if you have some power spectrum in the voids with some stochasticity, and then you calculate how, so only magnetic fields on very, very small scales, which are compared to oscillation length, only the reverse randomness magnetic fields on those scales will give you some constraints, and then you get, from future experiments, you get something like this. And this is actually, if you see, they were, even from current experiment, they were getting constraints which are of order 10 to the minus 4 if you square this. This is 10 to the minus 6.
And have these guys taken into account the effects that you would see from the galaxy?
No. No one before has, for CMB, no one has calculated the effects on
and
that.
For CMB, would that be an important effect?
Yeah, so that is this. That was this first plot.
So would it change their,
So
their
this,
calculations? Like
yeah. So so if we do their calculation slightly more accurately, I get this plot. So this is different. This is first plot. This is second. So here I am plotting also G square. g square in units of 10 to the minus 10 and nanogauss. So this plot you can compare with that plot. And this is for future experiments, which are much, much more sensitive than what they are considering. So the constraints are actually much weaker.
What's that X-ray bound coming from?
X-ray bound is coming from this X-ray observations of, I think, coma cluster. So they assume that, the X-ray emission is coming from some Bremsstrahlung. So you have some spectrum of X-rays that you expect, and they look for deviations from that.
That is much more model dependent than your
It is. So they assume some, yeah, so they have to,
your initial spectrum which you
so they are,
so that
yeah.
is, even if they are comparable, the CMB constraint is more robust.
Yeah, that's true. Okay, I think, yeah, so I'm at the end. So paper should appear on archive in, I think, a week or two. So again, the stochastic magnetic fields in the voids, people have done very simplistic things, which is probably wrong. So we should actually do some numerical evolution, which we are trying to do now. And in the future, so what I have shown is basically a toy model of galaxy. But hopefully in future we will have a much better handle on what the galaxy looks like, and then we will be more confident of what constraints we will get from. That's it. Thank you.
Regarding your plot of the galaxy and the pattern that you get, so as mass of axion increases, you move closer.
You come closer and closer to the galaxy.
So that gives you the range of masses in which you will be sensitive.
Yeah.
So what you
Yeah.
get from galactic center and what you get from
Right. So galactic center, it is, yeah.
these two patterns will merge at some 10 minus 12.
So,
Some value
sorry?
of mass, these patterns will merge.
No, which pattern? No, they will not merge.
These two patterns, yeah.
This.
Some mass,
Okay, yeah.
but
So,
this is as masses
so when you have mass where you are,
are
yeah, where you are in the galactic plane, then resonance is happening in galactic plane, and you will have signal here.
You told us about this mixing when you have a phi f wedge f axion type coupling. Suppose instead there was a phi times Maxwell f mu nu f p.
Yeah, so you have a scalar particle instead of pseudoscalar. So everything will remain same except that the polarization. So this resonance that we are getting, it is polarized, and it is polarized along the magnetic field direction that is transverse to the line of sight. So for a scalar particle, it will be polarized in a direction which is orthogonal to. So instead of this direction, it will be the orthogonal polarization that you will get. So by looking at,
basically will change, you're saying.
yeah,
More or less,
yeah,
I mean,
but
you switch polarization.
But looking at the polarization, you can tell whether it is a scalar particle or a pseudoscalar particle.
Are we connected to STS? Probably not. Okay, assuming that to be the case, and if there are no further questions, let's thank Rishi again.